Hi everyone. In today's video, we're going to talk about NeRF, Neural Radiance Field. We're trying to link concepts from the paper with pieces of code. So let's get started. So my first advice, don't be like me. If you're trying to read about NeRF, don't start from the neural net part, just start from the graphics part, because this whole thing is built on the advances of research in graphics field, not in neural net. In neural net, it's the basic thing. It's only MLP. When I started learning about NeRF, I looked at it as a neural network. Then I was confused. What are the training samples? What are the testing samples? Why they are optimizing for this and why they're not optimizing for that? So, but when I started reading about the graphics part of it, it started clicking, because the whole thing is built on research in graphics. So I have two notebooks here. This is the tiny NeRF, which you will find in the official GitHub repository, released with the original paper here. NeRF representing scenes as a neural radiance fields for view synthesis. But I don't recommend running this notebook because this was written in TensorFlow. The same research team has released an implementation in JAX, and you can find it here under Google Research, JAX NeRF. So this is the most recent implementation of the original NeRF, and most of the follow-up works were basically forks of this repository. So the research team now, they are not using TensorFlow, they are using JAX. So here's my notes. This is the original TensorFlow repository, and this is the JAX repository. These are follow-up works. So when we start understanding NeRF, you will notice that there are so many areas that you can improve. So this is what the same research team were working on. So this is a MIP NeRF and multi-NeRF. These are GitHub implementations. And these are the two main references for NeRF. The NeRF representing scenes as a neural radiance field for the view synthesis, and JAX NeRF, this is the GitHub implementation. So let's start with the most basic part, which is the whole thing was based on, the NeRF is based on volume rendering. So volume rendering is done by an algorithm called ray casting. So what is you have a volume in 3D, and you're trying to render that into 2D images from viewpoints, from cameras. So there is a good article from NVIDIA documentation. So volume rendering techniques. Jump all over here, you will find they basically explain the ray casting algorithm in a good way. In a sense, the role of optical model is to describe how particles in the volume interact with the light. For example, the most commonly used model assumes that the volume consists of particles that simultaneously emit and absorb light. So it's a formula of how particles in 3D space are interacting with light. More complex models incorporate local illumination and volumetric shadows, and they account for lighting scattering effects. Optical parameters are specified by the data values directly, or they are computed from applying one or more transfer functions to the data. So we're interested about this paragraph. So this is the key idea. Images are created by sampling the volume along all viewing rays and accumulating the resulting optical properties, as shown in figure 39. So for the emission absorption model, the accumulated color and opacity are computed according to equation 1, where Ci and Ai are the color and opacity assigned by transfer function of the data value at sample I. These equations are very similar. Basically, they are the same to the ones used in NeRF. Opacity Ai approximates absorption, and opacity weighted color Ci approximates the emission and the absorption along the ray segment between samples I and I plus 1, because you are tracking light, the light effect, and you want to for this to see how much light left. I know I'm not talking scientifically, but if you're shooting a ray, this ray passes particles, and each particle it passes, it's either it reduces the light, the energy of light. So you are trying to compute these between I and I plus 1. So you have the opacity A that tracks the absorption, how much light left, and you have the color based on the opacity. You are calculating the color, and along the rays, along all the samples in the ray, you can find the final color of the pixel in the image. So this is the key idea from volume rendering. It's samples affected by samples along ray. You're calculating the amount of light and how this will affect the color. This is the problem of volume rendering. The problem in NeRF is that you don't have 3D. You don't have 3D objects. So in volume rendering, you don't have 2D images. You're trying to render. You're trying to take images or create video of the 3D model in the scene. But in NeRF, you are trying to predict that 3D model. So in volume rendering, you have the 3D model, but you don't have the images. In NeRF, you have the images and you're trying to build the 3D model. And you might ask that what are the samples? Because in volume rendering, you know where are the samples, because the samples are there. They are in 3D. You know how they are affected by light. You know their position. Then you can calculate how to render. But in NeRF, you are trying to predict the samples. Where are the samples? So here is how I view the problem of neural radiance field. The input is a set of 2D images along with camera poses. So this is supposed to be 3, and these are 2 cameras. So you are shooting a ray from basically I'm visualizing it as 1 ray per camera, but it's not like that. It is each camera is shooting rays equal to the number of pixels. So all rays have the same origin, which is the camera position, but they are slightly directed towards the pixel. How it is viewing that object. So from each camera, you are shooting rays equal to the number of pixels, and along each ray, you are sampling points, and you're trying to match these points, to optimize these points to match the 2D images that you had before. So what is the ground truth in neural radiance field? The ground truth are the pixels in the training images. But what are the training samples? The training samples are the 3D points sampled along the ray. So you shoot a ray, you sample points, you adjust the color, then you calculate the final color of a pixel, and you compare that with the 2D images that you have from the training set. And based on that, you calculate the loss, you start updating the 3D points and the 3D scene, and change the colors until you match the pixels in the training images. So when I first read about it, I thought the training samples are the same as the number of pixels in the training images. But it turns out that's not the case. But NeRF is shooting 1 ray for each pixel, and along each ray, it samples, for small images, it samples 64 points. So 64 points times the number of pixels in each image times the number of training images. So this shows you why NeRF is so slow and why you have to install a GPU. And when I start to run NeRF, I tried to run it in a CPU, but it was extremely slow. I couldn't run. I only run the tiny NeRF, and you can see the results here are not so good. But I managed to run it on a CPU. So this shows you NeRF is a computationally heavy, and it requires so much computation power. So the loss in NeRF is how close are we to reconstruct the color for the ground truth pixel. All 3D points and the array contribute to the final color of the pixel. So you're shooting an array, you computed that using the volume rendering formula, and you compare that with the training samples. Objective: overfit the network as much as we can to match the colors in the training images. Test images can be used to test how the network performs on angles that are not present in the training set. So if you have test images in NeRF, basically you hold these out. You don't train on those, and you train on the training data. And when you calculate the loss for the training data, you render that test image, and you compare the rendered test image with the original test image, and you compare the loss. And this is your test accuracy. So you are testing the model from angles that are not present in the training data. So the testing concept is not present in NeRF because you're trying to overfit the model as much as possible to the training images that you have. So for another scene, even if you slightly change the coordinates, you need to train the NeRF from all over again. I think this will be an interesting research problem. So if you move the coordinates, how much you can transfer the same network with you. So the input of NeRF, it has to have the camera poses. This makes NeRF dependent on the structure from motion algorithms. The most known algorithm in structure from motion is ColMap, because if you don't have the camera positions, you don't know where to shoot the rays, and you don't know how to sample. Where are your samples? So you have to have the camera positions present along with your training set. So the training images and the camera's positions. NeRF is based on the volume rendering equations. So for rendering a model, you're shooting an array. This is the origin, this is the direction, and T is the sample. The final color of a pixel is basically dependent on the weights of the 3D points sampled along the array and their colors. So how much light is blocked earlier along the array? This shows the contribution for each 3D point along the array, and how much light is contributed by the array segment I. So these are the weights and these are the colors, and using this formula here, you're sampling points along the array. If you read the research in NeRF, this is the most active area, the sampling, because it's the core idea, and if you can accelerate this process, the whole network will be fast. So if you look into tiny NeRF implementation, you will find this is getRays function, this is render rays. Here you're computing the 3D points. Now you're running the network, and you're finding the sigma A, the opacities, and the color for each point. Then you are doing volume rendering. Here you're computing alpha, computing the weights. Then you are finding the RGB using the weights that's computed here in this formula. So this part here is basically performing this equation sample for all the 3D points in the scene. But you might ask how NeRF is sampling these points. It basically gives two values. Here they call it near and far, and using near and far, here you're sampling from normal distribution. And usually this flag here, brand, usually it's set to true, because you don't want the distance between all the samples along the array. You don't want it to be the same. You want to move the points you want to move the points a little bit, because you are at the end you are trying to render a continuous scene, and you don't know where are the volume points. So you are trying to mimic that distribution as much as possible by trying to add some randomness into the sampling process. Now here is one fundamental question about the sampling of NeRF. What if we sample a point that is in a void? There is no volume in there, or it's in a bad position. That's why NeRF is maintaining hierarchical volume sampling. It's important to mention that in tiny NeRF, here in this notebook, there is no coarse to fine sampling. Maybe that explains why I have a blurry view at the end here. Because the sampling is not good. But in practice, NeRF is maintaining coarse, so it samples points using the sampling process that I just explained, picking points along the array using near and far limits, and training the network on these 3D positions. Then using the important pixels, it try to adjust a probability distribution. Then it try to sample more points where there is a volume in there. So basically these points produces this probability distribution. Then in the second network, NeRF is sampling these fine points. So the orange points are the fine sampling. This is pretty much clear in the JAX implementation. So if you go to JAX implementation, you go to models. Here is the NeRF model. Number of coarse samples, number of fine samples. At the first, it trains coarse MLP, but then it starts the rendering from coarse points. Then it starts hierarchical sampling and train a second MLP, and at the end it appends the rendering from the coarse to fine sampling along with the coarse rendering. So this function here, NeRF model, it retains the rendering for coarse sampling and the rendering for both coarse and fine sampling. So MIP-NeRF explains the hierarchical sampling in a good way with the procedure for rendering a NeRF characterized by theta. Training a NeRF is straightforward. Using a set of observed images with known camera poses, we minimize the sum squared differences between all input pixel values and all predicted pixel values using gradient descent. To improve the sample efficiency, NeRF trains two separate MLPs, one coarse and one fine, where C is the observed pixel taken from the input image and R is the set of pixel rays across all images. Mildenhall et al. Construct T samples for coarse sampling by sampling 64 evenly spaced random T values with stratified sampling. The compositing weights composed by the coarse model are then taken as a piecewise constant PDF describing the distribution of a visible scene content, and 128 new T values are drawn from that PDF using inverse transform sampling to produce T fine. The union of these 192 T values are then sorted and passed to the fine MLP to produce the final predicted pixel color. So this wasn't present in Tiny NeRF because Tiny NeRF is just explaining the concept of NeRF, but you can see it clearly in the JAX implementation. Also, it's important to mention that in NeRF implementation, they are not passing the coordinates, the XY coordinates for the network. They are basically passing the positional encoding of these coordinates. I take this figure from a paper called Fourier Features, Let Network Learn High Frequency Functions in Low Dimensional Domains, where they showed that if you take the coordinates, you cannot perform vision tasks, But if you apply further features, you can achieve good results. So here it's blurry because you take the coordinates, the XY coordinates, but you can improve the vision task, by just plugging these features into further features. They implemented here in TinyNeRF, so they are using positional encoding for each 3D coordinates. So they are storing this function here, an embed function, and they are using embed function just before they run the network. Just to summarize what we have learned so far, NeRF first samples coarse points along the array, then use these coarse points to perform hierarchical sampling and train another MLP with fine sampling. And another thing, NeRF is not using the absolute coordinates. They are using they are plugging these coordinates into Fourier features, and they are using those in the network. Then next we want to learn the neural net part of NeRF, how they constructed the neural net. So here in this paper, Baking Neural Radiance Fields for Real-Time View Synthesis, they mentioned a great explanation of the NeRF network. A key design decision made in NeRF is to architect the MLP such that the volume density is only predicted as a function of a 3D position. So you use the 3D positions to predict the density, while emitted radiance is predicted as a function of both 3D position and 2D viewing direction. So you are trying to feed 5 things: X, Y, Z, the 3D coordinates, and theta and phi for the viewing direction. This is the position, this is the direction. And you're trying to predict the color and the opacity, sigma. So basically, you are not using these whole 5 to predict these 2. You are predicting sigma using the position, and you are predicting the color using the position and the direction. This is clear from the architecture they provided in the original NeRF paper. Yeah, here. So this is the architecture. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 layers, and you are feeding the position, and in the 5th layer you are concatenating the position, and in the layer before last, this layer here predicts sigma from the position, and it also concatenates the direction to predict the color. So this is the architecture of the NeRF network. It's a fairly simple architecture from a neural net perspective, but because they are using 2 neural nets, this makes it very slow to train. So how to evaluate the performance of the neural net? Because even if you render for a test image, you can't just look at both images and give a score. So you need an evaluation metric. And if you read some research papers in this field, you will notice that they are usually using 2 metrics. One called PSNR, peak signal to noise ratio, and SSIM, the structure similarity index measure. So PSNR, I took this definition from Wikipedia. It measures the mean squared error between an image I and a reconstruction. It's usually used in a compression and a reconstruction K. And then it's just performed this formula here, where max I is the maximum value in a pixel. SSIM measures the similarity between patches. So given 2 patches, X and Y, it performs this formula here. But the one they used in TinyNeRF is the PSNR. So you can notice that they are using PSNR for evaluating the training. But when I looked at the PSNR implementation here, I only found -10 the loss, which is the mean squared error, divided by log of 10, and it didn't basically match with the formula that I found in papers and in Wikipedia, because this is the formula. You have to perform a 20 log to the base 10 of maximum value in an image, -10 log to the base 10 MSE. So I found this is very confusing, because it seems that they are only taking this part here. It's the basic math problem where people are usually skip some steps, and when they skip one step, you are completely lost. It turns out that they assume that the maximum pixel value in an image is 1, and log base 10 for 1 is 0, so this cancels this term here, and you're left with this one. But why do you have to divide? I didn't see any division here, so I have to do it myself. So if you use this rule here, this is basically calculus. I missed that in my calculus class. Log of b to the base a, you can separate it into a fraction, where the base can be in the denominator, and you can replace it with the same base in the numerator and denominator. So here they used it for both sides, and because log of 1 equals 0, they are left with this formula here. I found this solution here is elegant, because you're basically dividing by the log function, and you don't know in the library they are using which base they are using. Are they using base 10 or they using the natural E? Because this is the most confusing part. You read in the paper log, they usually skip the part where they mention the base, and they assume that you know it, but you don't know it, and you don't know. In computer science, I rarely see log to the base 10. I'm usually confused. Is it to the base natural E or 2? So this is the most confusing part, and different libraries have their different implementations. So here, how is it implemented in Tiny, NeRF, and in the JAX implementation? You can go to the utilities and look for the function that computes the PSNR. Here, it returns the same formula with JAX and NumPy data type. So computes PSNR value given MSE. We assume the maximum pixel value is 1. So this is the assumption that removes the entire term from the equation. So here is the Tiny NeRF implementation. I think changed some. I definitely adds this part because it throws an error here between Keras and TensorFlow. There is a dependency that I couldn't understand, and I found this solution on Stack Overflow. No, this was basically this was a suggestion from the Copilot. They could not call it Copilot, Gemini on the Colab. So this was an LLM suggestion. It uses Tiny NeRF data with 100 images with their poses and focal. And I changed some parts just to make it run on Colab CPU. This used to be 64, I changed it to 32. This is the number of cores sampling along the array. And this, I think this directly affects the resolution, because the more you sample, the more accurate you reconstruct the 3D. And because of that, I have this blurry video at the end. Along with that, I don't have a fine MLP. It's only the coarse MLP is implemented here in Tiny NeRF. So I run this for 2,000 iterations. At the beginning, you just start with a dark scene where all the 3D positions have random values, then you start seeing the network is actually learning something until you go to the end, and you end up with the PSNR around 22. And this is the video. So how to improve this? You add more samples and you add a fine MLP to this implementation. So at the end of this video, you will probably notice that there are some weaknesses with NeRF. So that it trains 2 MLP. The sampling, there is an improvement for sampling process, and it trains on a small images. And this is basically where the research is directed. They either playing with the sampling, they are improving the sampling, they are trying to get rid of the coarse MLP, or they are trying to accelerate it. And they are also they're trying to accommodate larger scenes for more resolution. So these are the 3 main directions that are initiated by the original NeRF paper. Also, there are some efforts to change the rendering process completely. So the Gaussian splatting, which is much faster than NeRF, it doesn't follow this ray casting technique. It's basically initialize Gaussians in the 3D and try to optimize these Gaussians to match the 2D images. So these are the research directions. Either you're improving NeRF by accelerating NeRF, because each part you are doing, you're accelerating NeRF, or you're just scaling NeRF to new scenes, larger scenes, or scenes with more details. This is an improvement. Or basically you're following a different technique. These are the research directions. That's it, guys, for today's video. If you find this video helpful, please like and subscribe. I'll make sure to link these notes in the description below, and that tiny NeRF, you can find it in the original GitHub implementation. Thanks for watching. Bye.